Welcome to the new era of video creation with Bayo Z8. This is our new series on AI teaching natural language processing. Today, we will discuss the machine translation. Here are the contents. Machine translation, MT, is the process of using software to translate text from one language to another. Over the years, MT has become crucial for tasks like global communication, content localization, and breaking language barriers in everything from websites to technical documents. While human translation is based on deep cultural and contextual knowledge, MT systems rely on algorithms to generate translations. The main challenge for MT is not only translating words accurately, but also ensuring that the translation sounds natural and preserves the original meaning, tone, and context of the source text. As you'll see throughout this lecture, this is where the complexities and advancements in MT come into play. Machine translation can be approached in several ways. Rule-based machine translation, RBMT, the earliest form of MT, where translation is governed by a set of linguistic rules. These rules are paired with dictionaries to convert sentences from one language to another. While RBMT provides controlled and understandable translations, it often struggles with idiomatic phrases and contextual meanings. Statistical machine translation, SMT. SMT represents a shift from rule-based methods. It relies on statistical models derived from large bilingual corpora of parallel texts. The system learns from these corpora how phrases in one language correspond to those in another. While SMT is more flexible, it often produces less fluent translations and has difficulty with rare or unseen phrases. Neural machine translation, NMT. NMT leverages neural networks, particularly deep learning models, to produce more fluent and contextually accurate translations. With the help of large-scale datasets, NMT systems like transformer-based models, e.g., BERT, GPT, have revolutionized MT in recent years. Hybrid systems. These systems combine the strengths of RBMT, SMT, and NMT. For example, an NMT system might be combined with rule-based corrections to improve translation accuracy, especially for specialized content. Rule-based machine translation, RBMT, relies on predefined sets of linguistic rules for translating text. These rules include grammatical rules, syntactic structures, and vocabulary pairs, all stored in dictionaries. When a sentence is translated, the system applies these rules to perform the conversion. While RBMT provides understandable translations and is especially useful for specialized domains like technical or legal content, it faces significant limitations. The system struggles with translating idiomatic expressions and contextual nuances, as it cannot easily adapt to ambiguous language. For example, it would have difficulty translating a sentence like kick the bucket, which has a non-literal meaning. Statistical machine translation, SMT, marked a significant shift from rule-based approaches by relying on bilingual corpora, large collections of text in two languages that are paired, parallel texts. The system learns how words and phrases in one language correspond to those in another by analyzing statistical relationships. SMT models do not rely on rigid rules, making them more flexible than RBMT. However, these models still struggle with fluency and idiomatic language. For example, the translation of a sentence might be accurate word for word, but may not sound natural in the target language. SMT models like IBM Model 1 and phrase-based SMT have been widely used, with Google Translate relying on SMT prior to the advent of neural models. The introduction of neural machine translation, NMT, represents the most significant advancement in MT in recent years. NMT uses deep learning techniques, particularly neural networks, to translate text. Unlike previous methods that focused on translating words or phrases individually, NMT translates entire sentences at once, making it more context-aware. Early NMT models relied on recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, which excel at sequential tasks. However, the most groundbreaking development came with the introduction of transformer-based models like BERT and GPT, which significantly improved translation quality. NMT is better at understanding complex sentence structures, idiomatic language, and context. This method offers more fluent, natural-sounding translations compared to previous techniques, marking a major leap forward in machine translation. At the core of most NMT systems is the encoder-decoder architecture, a neural network setup that transforms source text into a target language. Here's how it works. Encoder. The input sentence is first passed through an encoder, which converts the source language into a vector, a numerical representation of the text's meaning. Decoder. The decoder takes this vector and generates a corresponding output in the target language, one word at a time. Attention mechanism. One of the critical innovations in NMT is the attention mechanism, which allows the model to focus on specific parts of the input sentence while generating the translation. For example, in translating long sentences, the model can decide which words or phrases in the source sentence are most relevant to the current word being translated in the target language. This architecture, particularly in transformer-based models, significantly improves the fluency and accuracy of machine translation. The advent of transformer models has fundamentally transformed machine translation. Unlike RNNs and LSTMs, which process text sequentially, transformer models can process entire sentences in parallel, leading to much faster and more efficient translations. The key innovation is the self-attention mechanism, which allows each word to focus on other relevant words in the sentence. Transformer models like BERT and GPT have set new benchmarks in language understanding and generation. These models have become the backbone of modern MT systems, including Google Translate and other high-performance translation services. The ability to handle large amounts of text data and learn complex relationships between languages has led to significant improvements in translation quality. Despite its advancements, machine translation still faces several challenges. Ambiguity. Many words have multiple meanings, and without context, MT systems can misinterpret them. For example, the word bat could refer to a flying mammal or a piece of sports equipment, and determining the correct translation depends on the context. Cultural differences. Idiomatic phrases, humor, and cultural references often don't translate well between languages. Phrases like break a leg, used to wish someone good luck, can be confusing in another language. Resource limitations. Some languages have fewer bilingual corpora available, making it harder for MT systems to train effectively for those languages. Evaluation. Evaluating the quality of translations is challenging because it's inherently subjective. While human translators can intuitively assess the fluency and accuracy of a translation, automated evaluation metrics like BLEU score have limitations. To evaluate machine translation quality, several automated metrics are used. BLEU measures the n-gram overlap between the machine-generated translation and a reference translation. BLEU is widely used in MT research but has limitations in capturing contextual meaning. Meteor. It considers synonymy and stemming, base forms of words, making it more sensitive to variations in language compared to BLEU. TR. Measures the minimum number of edits, insertions, deletions, substitutions required to convert a machine translation into the reference translation. Human evaluation. While automated metrics are useful, human evaluation remains the gold standard for assessing translation quality, as it considers factors like fluency, accuracy, and context. Machine translation has a wide range of applications, including real-time translation. Services like Google Translate now offer real-time translations for chats, emails, and even social media, helping break language barriers in communication. Content localization. MT is essential for website localization, allowing companies to easily adapt their content for global markets. Cross-lingual information retrieval. MT helps search engines deliver relevant results in different languages, enabling cross-lingual search. Language learning. MT tools are widely used in language learning apps, providing translations and helping users understand foreign languages better. While NMT systems have achieved great success for widely spoken languages, low-resource languages with limited bilingual corpora pose a challenge. NMT systems need large parallel datasets to train effectively, but such datasets are often unavailable for these languages. However, techniques like transfer learning and multilingual models can help. For example, MBART, multilingual BART, is a model trained on many languages simultaneously, enabling it to leverage knowledge from high-resource languages to improve translation quality for low-resource ones. Looking ahead, several trends are shaping the future of machine translation. Better contextual understanding. As models are trained on larger, more diverse data sets, their ability to grasp context and nuances in language will continue to improve. Multilingual models. The development of multilingual models will make it easier to translate across many languages simultaneously, improving efficiency and accuracy. Zero-shot translation. Advances in zero-shot translation allow models to translate between languages, even if they have not been directly trained on those language pairs. Ethical concerns. As MT systems become more widespread, issues like bias in training data and privacy of user data are becoming increasingly important. One significant challenge in machine translation is handling domain-specific language. Fields like medicine, law, and technology often have specialized terms and jargon that may not be accurately translated using general-purpose models. To address this, domain-adapted models are fine-tuned with specialized bilingual corpora from those specific fields. For example, a legal MT model would be trained on legal documents to better handle legal terminology. This fine-tuning can significantly improve translation quality for technical texts. As with all AI technologies, machine translation must be used responsibly. A few key ethical concerns include bias. MT systems can inherit biases from the data they are trained on, leading to translations that reflect gender, racial, or cultural biases. Stereotypes. Some translations may inadvertently reinforce harmful stereotypes or inaccuracies. Privacy. When translating sensitive or personal content, it's essential to ensure privacy and data security. Fairness and transparency in MT systems are crucial for ensuring that all languages and cultures are represented accurately and ethically. In conclusion, machine translation has come a long way, especially with the rise of neural machine translation, NMT, and deep learning techniques. While we have made significant strides in improving translation quality, challenges remain, particularly with low-resource languages, domain-specific translations, and addressing ethical concerns. Looking ahead, we can expect further advancements in multilingual models, zero-shot translation, and techniques that handle cultural and contextual nuances. The future of MT promises to break down language barriers more effectively, but we must continue to address challenges related to fairness, privacy, and the need for large data sets. Thank you for your attention. Let's open the floor for questions or discussion.